The automotive suspension system faces a fundamental engineering paradox: how to simultaneously isolate occupants from road irregularities while maintaining consistent tire contact for optimal control and safety. This inherent conflict defines the core challenge in its design. Early vehicle designs relied on rudimentary spring elements, often simple leaf springs, with minimal or no damping. This approach produced a compromised ride quality, characterized by excessive body motion and limited wheel control, especially over uneven terrain, directly impacting stability and driver fatigue. The role of springs is to absorb and store kinetic energy from road inputs. Without a mechanism to dissipate this stored energy, the vehicle would enter a perpetual cycle of oscillation, leading to an uncontrolled ride. This phenomenon highlights the critical need for energy damping beyond simple spring action. Dampers, commonly known as shock absorbers, are engineered to counteract this oscillatory behavior. They convert the kinetic energy of suspension movement into thermal energy, which is then dissipated. This controlled resistance to motion stabilizes the chassis, ensuring the tires remain firmly pressed against the road surface. A pivotal architectural decision in suspension design involves the choice between dependent and independent systems. Dependent suspensions, such as a solid axle, link the wheels on the same axle, causing the movement of one wheel to directly influence the other. This simplicity often sacrifices ride comfort and handling precision compared to independent designs. The MacPherson Strut, a widely adopted independent suspension design, integrates the spring and damper into a single, compact unit. This configuration simplifies vehicle packaging and reduces unsprung mass. However, its geometry can introduce undesirable camber changes during suspension travel, affecting tire contact patch. Double wishbone suspension employs two triangular or A-shaped arms, known as wishbones, to precisely control the wheel's vertical movement. This design offers superior control over camber, caster, and toe angles throughout the suspension's range of motion, significantly optimizing tire contact and enhancing dynamic handling. Its complexity, however, demands greater packaging space. Multi-link suspension represents a further evolution of independent designs, utilizing multiple individual links to connect the wheel hub to the chassis. This arrangement allows engineers to independently fine-tune various geometric parameters, achieving an optimized balance between ride comfort, precise handling, and straight-line stability, albeit at a higher manufacturing cost. Torsion bar suspension offers an alternative to conventional coil springs by employing the torsional elasticity of a steel bar. This design can provide packaging advantages and adjustability. However, its inherently progressive spring rate, where resistance increases nonlinearly with deflection, can sometimes result in a less compliant ride compared to linear coil springs over minor imperfections. Anti-roll bars, or sway bars, are critical components designed to mitigate body roll during cornering. They function as a torsional spring connecting the left and right suspension. By resisting the relative vertical motion of the wheels, they increase the vehicle's roll stiffness, distributing load more effectively to the outside tires, without compromising straight-line ride quality. Beyond passive components, active and semi-active suspension systems introduce dynamic control. These advanced setups use sensors to monitor road conditions and driver inputs, coupled with actuators to continuously adjust damping forces and sometimes spring rates in real time. This adaptability dramatically improves both ride comfort and handling performance, but at a significant increase in complexity and cost. The components within a suspension system are subjected to immense and repetitive dynamic loads. Material selection is therefore critical, often involving high-strength steels, aluminum alloys, and advanced composites to minimize unsprung mass, resist fatigue, and maintain structural integrity. Bushings, bearings, and various mounts are also vital for isolating noise, vibration, and harshness. A crucial distinction in suspension dynamics lies between sprung and unsprung mass. Unsprung mass refers to components not supported by the suspension, such as wheels, tires, brakes, and parts of the suspension arms. Minimizing unsprung mass is paramount, as it allows the wheels to react more quickly to road irregularities, enhancing grip and overall ride quality. The design of any automotive suspension system inherently involves navigating a complex web of trade-offs. Optimizing for ride comfort often means compromising handling precision, while prioritizing high-performance handling can detract from occupant isolation. Engineers must reconcile these conflicting demands with considerations for cost, packaging constraints, and long-term durability. The future of suspension systems will likely feature greater integration with overall vehicle control architecture, incorporating predictive capabilities based on navigation data and environmental sensors. The advent of autonomous driving will place even more stringent demands on suspension to provide consistent stability and occupant comfort across an even wider range of operating conditions and road surfaces.